everyone, and welcome back. Now, this lecture series is called Chaos Theory, and a few times through the lecture series I will refer to something as chaotic, but you will be keen to notice that I have never actually told you what it means to be chaotic. This is not one of those things where if you see it, you know it. There has been a precise mathematical theory developed to understand chaos, and we have been building towards that through this lecture series. Now, a lot of the sort of arguments and battles over what it means to be chaotic were had throughout the 1980s in the mathematical literature. In this lecture series, I'm going to provide to you the definition of chaos that was given to us by Bob Devaney. Again, I've spoken about Bob Devaney before. He is one of my mathematical heroes. He is one of the pioneers of chaos theory and really, a quantitative understanding of what chaos actually is. And so we're going to use his definition of chaos. Now, I'm not using this because I'm biased. I'm using this because this is now sort of the dominant way that we understand chaos. This is the primary definition for chaos. The only other definition that still persists, at least from my perspective, and there could be, gaps or blind spots here, is a positive Lyapunov exponent. Now, I've done a lecture series on Lyapunov exponents before. It turns out that you can get positive Lyapunov exponents for things that are not chaotic in the sense that we would think about them as being chaotic. And so it's a little bit of a flawed metric. Now, here's the problem. So is Devaney's definition of chaos. There is, since Devaney actually gave his definition of chaos, there is a whole lot of work to show that some of the points in the definition imply certain other points under certain conditions, that you could have maybe something that wouldn't necessarily be chaotic in a traditional sense that can still satisfy many or all of these conditions. So everything is flawed here, but I think that Devaney, through his definition of chaos, really captures the essence of what it means to be chaotic. Okay, so that's enough talking. Let's actually do. And I'm going to start with a definition, okay? So we're going to do a lot of definitions today, and that's because we are going to be working towards defining chaos. So we're going to say that a function from, in our case, a one-dimensional set back into a one-dimensional set. We'll take J to be an interval, for example. But of course, everything we do here can extend to higher dimensional systems as well. This is said is topologically transitive. Okay, so here's our definition. It's topologically transitive if for all u and v in J open sets. Okay, so again, if you're familiar with topology, you know that topology is really the sort of language of open sets. A topology, by definition, is telling you what is an open set. If for all u and v open sets, there exists an n greater than or equal to 1 such that the nth forward image of the open set U intersects with that other open set V. Okay, so think about what this really means, okay? I could take U and V to be really, really tiny little intervals, for example, open intervals. Maybe I could have them as length 1/1,000,000, okay? So what it says is that if your mapping is topologically transitive, it says that you can always push one of these things forward, and U and V are arbitrary, so you can switch where they appear in here. You can always push the image of the open set forward, and you will wind up intersecting the other open set. In some sense, this is like a mixing up criteria, right? It says that nobody is isolated here. If you have distinct open sets over here and over here, eventually they get thrown and mixed up together. Now, I'm going to provide a little bit of a comprehensive understanding here that is not fully true, but it's a good way to think about things. I did a previous lecture series on the basics of ergodic theory, and we saw that ergodic theory is really measure theoretic dynamical systems analysis. It's statistical in some sense. Now, what I provided for you is the definition of an ergodic measure. An ergodic measure says that there are sort of no sets left behind as well, right? And this is done in the probabilistic sense of, almost everywhere, measure zero sets, etc. but it says that the domain is undecomposable. Effectively, this is the topological characterization of exactly the same thing. It's saying that your domain cannot be split up, right? If you start looking at little subsets of the domain, they eventually get all mixed together, okay? There's no separated pieces for your domain here. So I like to think of this as a topological characterization of ergodicity. Now, there are differences and subtleties to both of these things, but it's a nice way to at least get the juices flowing. Now, here's the one that I want to talk about as well. I want to give you another definition, and this is the definition that, this is what people think of when they think of chaos, right? I'm going to talk about sensitive dependence on initial conditions, right? So maybe we're starting to think about maybe Jurassic Park or something like that. Let's again take a map from J to J, so interval to interval, but of course you can do this in higher dimensions. And we'll say that this thing has sensitive dependence on initial conditions Okay, so if there exists a delta greater than 0, so a small number potentially, such that for every point in J, and any neighborhood, now neighborhood is sort of mathematical slang for open set, right, or ball around the point. Any open neighborhood, I'll say n of x, so n stands for neighborhood centered at x, then there exists a y in this neighborhood, so these can be smaller and smaller and smaller essentially, and an n greater than or equal to 0 such that the forward iterates of these things are eventually separated by delta. Okay, so what this says is that you could take a very, very, very tiny neighborhood around a point, and you can always find something in there that will be separated by at least a distance of delta after some forward number of iterates. Effectively, this is telling you that trajectories separate, right? Now, it's very important to read this and really understand it. It doesn't say every point in the neighborhood separates. It just says that there has to be one, and you can make that neighborhood smaller and smaller, okay? Now, there are many, many systems that exhibit sensitive dependence on initial conditions that are not chaotic. Let me give you an example, okay? So here is a really simple map. I'm going to go from R to R here. So it's bigger than an interval, but that's okay, by 2x, okay? Now, all this map does is take a point and multiply by 2. So you can imagine you take two nearby points. They're separated by a distance of, say, epsilon. Then after one iteration, they're separated by 2 epsilon, 4 epsilon, 8 epsilon, 16 epsilon. They just keep getting further apart. So clearly, we have sensitive dependence on initial conditions. But I think that, without me even giving you a definition of chaos, you'd be hard-pressed to call this a chaotic map. I mean, it's extremely predictable. I know exactly what's going to happen, as opposed to, say, like our Cantor set dynamics we've looked at already. In particular, this does not have the topologically transitive property. So here's another example. Let's go back to our Cantor set. Let's go, sorry, I think I was using capital F, so let's keep that notation consistent. Let's use our old faithful here, the logistic map, when, remember, mu is bigger than 2 plus the square root of 5. This was a point where we had that Cantor set. We use symbolic dynamics to quantify it. Well, the way that we can show that this thing has sensitive dependence on initial conditions is the following. Let's pick x and y in the interval 0 to 1, intersected with lambda, of course, and not equal to each other. All right? So if they're not equal to each other by the homeomorphism established by symbolic dynamics, this is the same as saying their itineraries are not the same either, right? But if their itineraries are not the same, then eventually putting these two things forward, right? So there's a point maybe where S has a 0, where Y has a 1, or vice versa, which means they're on opposite sides of 1/2, right? Now remember, we had this set A0 that splits the interval 0 to 1, right? Remember A0, if you go back through your notes from a few lectures ago, A0 was the point in the middle of this thing that gets mapped out of the domain. So if this was 1 right here, A0 was this big piece, right? And so by the itineraries, what we can see is that you're either going to be over here or over here. So it means that we can take delta equal to the length of A0. Because if these two things have different itineraries, then they're on opposite sides of this interval A0, and therefore they're separated by the length of A0. So that's an immediate way that we can see this using the symbolic dynamics. Now, let's actually give the definition of what it means to be chaotic, okay? So let's say, let's keep going like this. Let's say this thing is chaotic. And this doesn't necessarily have to be an interval. For example, it could be my little Cantor set, right? So I'm being sort of purposely vague here again. It's chaotic on J if, okay, 1, F has sensitive dependence on initial conditions. This sensitive dependence on initial conditions is also colloquially known as the butterfly effect, right? So, you know, if a system is initiated just slightly off, you know, if a butterfly just flaps its wings and generates a little bit more wind, then you have drastic consequences. That's effectively what this is saying right here. F is topologically transitive. And in that case, that means that you're sort of mixing up through the whole domain. You know, nobody gets left behind. And we could, for example, go back to this system. We could see that that thing is topologically transitive just by the existence of a dense orbit that we proved in the symbolic setting, right? And then number 3, the only definition we didn't give today is periodic points of F are dense in J. This is something we've also talked about already, right? We already proved that the periodic points are dense in the logistic map on this lambda set. We also did it for the shift map. So let's actually just apply this right out of the gate. This logistic map on lambda for mu greater than 2 plus the square root of 5 is chaotic. Okay, so I kept calling it chaotic, but I didn't really explain to you why it's chaotic. Well, here now you know. This guy is not chaotic because its periodic points are not dense, right? It only has one fixed point at x equal to 0, so not a chaotic mapping. The shift map is chaotic. We established the topological conjugacy with the existence of a dense orbit, and I'm going to leave that as an exercise for you to prove. If you can find a dense orbit, then you're topologically transitive, and that's an if and only if statement. And let's actually do another example. Let's sort of piggyback on this one, but let's do it in a different way. We actually saw this, I think, in the very first lecture, or maybe the second lecture. Let's go from the circle back to itself by f of theta is equal to 2 theta, okay? So this is an angle doubling map, right? So it says that if you give me, here's my circle S1, if you give me an angle on this thing, theta, then what's going to happen is that's going to get doubled into 2 theta. And so, of course, what we just spoke about here, you can easily prove that this thing has sensitive dependence on initial conditions because it multiplies the error by 2 every single time you go through. In fact, This holds for every y in the neighborhood, not just one. This thing, its periodic points are dense in the circle. This was spoken about, again, in the very first time I mentioned this. I'm going to leave it as an exercise for you to characterize these things. Maybe go back to your notes. You'll see I gave you what all of these periodic points look like in here, but you can easily sort of calculate this out as well. And it's topologically transitive. This is maybe the slightly harder version of this, or the hardest thing to prove. But let's actually just do this. Let's say let U be an interval, for example, in S1, right? So the topology of open sets on the circle is generated by these little intervals. So I'll just say, like, maybe this is my little interval, for example. Okay, so then if the length of U is equal to epsilon, this implies that the length of f of U is equal to 2 epsilon. And this implies that if I keep going forward, this is 2 to the n times epsilon, okay? But think about what's happening. My interval is getting bigger and bigger and bigger and bigger. Now the whole length of the circle, the circumference, is only 2 pi. So that means that I can always find an n big enough so that this interval will eventually cover the whole circle. And therefore, this forward iterate will intersect with everything else because it's covered the whole circle. So that means that this thing is also topologically transitive. And this really comes from the compactness of the circle, the fact that I can go around. This guy is not topologically transitive because it's going over the whole real line, right? So it just keeps stretching itself out, but it never actually covers the whole real line. Okay, as a sort of final demonstration, and of course, what follows through the rest of this lecture series is, applying this definition and using it to really characterize interesting problems. But let's do one more. Let's look at an example from the logistic map where the dynamics actually exist on a non-null set. And what I mean by a non-null set is, like, this Cantor set, computationally, you'll never find it, right? If you try to simulate this mapping with mu bigger than 2 plus the square root of 5, everything that you put into the computer is going to minus infinity. And it's because this is such a tiny set. I kept referring to it as dust. That's a good way to think of it. Let's do the logistic map now, but with mu is equal to 4. So we're below this threshold. And I'm going to say this thing is chaotic on the whole interval 0 to 1. So not a Cantor set, a gigantic set. And the beauty here is that, if I pick a number between 0 and 1, I can iterate this thing and I can see the chaos. I can feel it. I can touch it, right? So how are we going to prove this? We're actually going to prove it with topological conjugacy. What we're going to do is we're going to show that it's actually conjugate to the shift map on the circle. And because I just established that the shift map is chaotic, well, it turns out that chaos is preserved by topological conjugacy. And this should make sense because topological conjugacy preserves dynamical structure. Being chaotic is dynamical structure. But of course, you can prove this as well if you wanted to. So let's say let g of theta equal to 2 theta on S1. So basically, let G denote this guy up here. And then we're going to define another function. We're going to call it H1, which maps the circle into the interval -1 to 1 by H1 of theta is equal to cos of theta. Okay? So that is the H1 function is the projection of the circle onto this interval -1 to 1, right? So that's this piece right here going back and forth, okay? And then I'm going to do this with a couple different pieces. I'm going to let q of x be 2x squared minus 1, okay? All right, now let's take a look. H1 of g of theta is equal to cos of 2 theta. Okay, so that's just a composition. This is of, not an O. Which, let's have a little bit of fun. Let's use a double angle formula. You're on the internet right now. Pause the video, look up some trig identities, have a little bit of fun with this. You know, I'm not doing this to torture you, to make you do the work. I think that doing the math is actually the fun part. And of course, I want you to have the fun too. But this becomes 2 cos squared of theta minus 1, which is the same as q of h1 of theta. Okay? So this means h1 conjugates g and q. Now what we're going to do is we're going to do something very similar. So similarly, you can also show that f4 of h2 is equal to h2 of q, where h2 of, let's say, t for a dummy variable is 1/2 of t minus 1. So it's a linear, 1 minus t, pardon me. Let's just put a minus there so that I don't have to erase it. This is just a linear gradient. It's a completely invertible function. All it does is take you from this quadratic function to this quadratic function. And effectively, what have we done? Well, let's take a look. I had S1 being mapped into S1 by G. Then I had -1 to 1 being mapped into -1 to 1 by Q. And then I had 0 to 1 being mapped into 0 to 1 by F4. And if we take note of this, I had H1 mapping me between these two pieces, and H2 mapping me between these two pieces. So Q is topologically conjugate to F4, which means that F4 is also a chaotic mapping, right? And so effectively, we got a 2-for-1 bargain here, right? We got not only that F4 is chaotic on 0 to 1, but we also found that Q is chaotic on -1 to 1. This is very similar to what we saw with symbolic dynamics, right? Symbolic dynamics were a weird way of characterizing, what felt like just a fun math problem, but turned out to be how we understood that this was chaotic on the Cantor set. Well, again, this feels like a weird artificial map, and at least from my perspective, it feels like these two things have nothing to do with each other, right? I wouldn't have guessed without maybe seeing the answer here. Somebody very clever came up with this. But look at this. This guy was relatively easy to use. I proved that it was topologically transitive. I mean, okay, mostly with words, but it was a pretty easy way of thinking about it. Similarly, finding its periodic points was pretty easy, and proving sensitive dependence on initial conditions, again, was super easy. But this guy right here, much harder, right? Prove that its periodic points are dense. I mean, that's a hard problem to do. It's even a hard problem to do in Q. Prove that it's topologically transitive. Hard. Prove that it has sensitive dependence on initial conditions. Hard. Conjugacy made it easy. So I've said this before in this lecture series, but topological conjugacies are one of my all-time favorite things in mathematics. It's like those in bifurcations, and in fact, those two things are actually related, as we're going to talk about later. But check out the heavy lifting that's been done here by topological conjugacies. It's really given us all of the information we needed just by establishing these relationships and these composition relationships, these commuting relationships between these two, or three in this case, mappings. We're going to keep carrying this through. Now you know when I talk about chaos, you're able to say, oh yes, okay, now I know what Jason's talking about. When he says that something's chaotic, he means it has sensitive dependence on initial conditions, so the butterfly effect. It's topologically transitive, so it's indecomposable, right? There's nothing in the space I can forget about. And its periodic points are dense, right? So when we talk about dense sets, these are sets you can approximate things with, like we saw with the shift space, like we see with the rationals inside of the reals. So when we come back, we're going to start talking about structural stability. This is, if I can bend or break mappings while preserving their dynamics. So I'll see you all in the next video, everybody.